Okay, this week I want to talk about two more convergence tests, and then we're going to work on some power series and move on to integration before the end of the week. Okay, so the next two convergence tests I want to deal with are when we have a monotonically decreasing sequence. So the first one is going to be Cochise condensation test. And this theorem starts out with a monotonically decreasing positive sequence. So suppose a sub 1 is bigger than an a sub 2, bigger than ... bigger than or equal to 0. So the sequence decreases. It might decrease to 0, it might not decrease to 0. But what the statement of the theorem is the sum of a sub n from n equals 1 to infinity converges if and only if the sum from n equals 1 to infinity of 2 to the k a sub 2 to the k converges. Okay, so we'll prove this in a second, but you might recall from an earlier video we showed that the harmonic series, the sum of 1 over n, diverged, and we did that by looking at, well, the first term, and then the next two terms, and the next 4, and the next 8, and the next 16, and so on, and showed that that was unbounded. So since that was bigger than the harmonic series must also have been unbounded, therefore it diverged. That's what this test does. So let me show you just that quick example again. The sum 1 over n from n equals 1 to infinity diverges because the sum from n equals 1 to infinity of 2 to the k times 1 over 2 to the k is equal to the sum from n equals 1 to infinity of 1 diverges. Okay. So let's prove this. So since each a sub I is bigger than or equal to 0, we have a monotonic sequence of partial sums. So we just have to worry about boundedness. Because we know that a monotonic sequence converges if and only if it's bounded. Okay, so let's look at the partial sums of both sequences. Let's look at S sub n equal to a sub 1 plus a sub 2 plus ... a sub n, and let's say t sub k is equal to a sub 1 plus 2 a sub 2 plus 4 a sub 4 plus ... plus 2 to the k a sub 2 to the k. Okay. Then for n less than 2 to the k, S sub n is less than or equal to a1 plus a2 plus a3 plus dot 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 plus a sub 2 to the k plus dot 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 plus a sub 2 to the k plus 1 minus 1. Okay, so S sub n is, well, n is smaller than 2 to the k. So S sub n is add up the first 2 to the k of them. So S sub n would just be adding up these guys. I've added some more to there, so I've got that less than or equal to sign. If these guys were all 0, then it would be equal to. Okay. But this is, by monotonicity, less than or equal to a sub 1 plus, since a sub 3 is smaller than a sub 2, the term on top is smaller than 2a sub 2, and that's what we're going to do for all of these. We'll take the first one. This guy is the biggest of all of these. There's 2 to the k of them, so this is going to be smaller than or equal to 2 to the k times a sub 2 to the k, which is equal to t sub k. So S sub n is less than or equal to t sub k. Okay. That means if t sub k is bounded, S sub n is bounded. And if S sub n is unbounded, t sub k is unbounded. Alright, that almost gets us there, but that's not quite an if and only if, because I could have that S sub n is unbounded, but t sub k is bounded, because S sub n would be bigger. Alright. Sorry. The other way around. I could have that t sub k is unbounded, but S sub n is bounded. So now I have to show a inequality with some function of S sub n on top and some function of t sub k on bottom. So, if n is bigger than 2 to the k, then S sub n is bigger than or equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot 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 plus, well, I'm not going to add more terms, I'm going to take away some terms. So a sub 2 to the k minus 1 plus 1 plus dot 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 plus a sub 2 to the k. Okay, and that's bigger than or equal to a sub 1 plus, well, half of a sub 1, because I'm going to make the top thing bigger, so I'm making this smaller. I'm making that guy half as big, plus a sub 2 plus 2 times a sub 4. A sub 3 is bigger than a sub 4, so this is bigger than 2a sub 4 plus dot 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 plus 2 to the k minus 1 times a sub 2 to the k. Now each of these is half as big as what it would be in t sub k, so this is equal to 1/2 t sub k. So 2s sub n is bigger than or equal to t sub k. So if t sub k is unbounded, s sub n is 2, and if S sub n is bounded, so is T sub k. So S sub n is bounded if and only if T sub k is bounded. So by monotonicity of both, they converge if and only if they both converge or both diverge. Okay, so that's Cochise condensation test. That's 3.27, I believe. Yeah. That's theorem 3.27. The other theorem that I want to talk about with monotonic sequences and positive values is the alternating series test. So let's write this theorem. Let C sub n be bigger than 0 and C sub n decreases to 0. So with C sub n bigger than C sub n plus 1, bigger than or equal to ... for all n, let's just say. Then, so I've got positive coefficients, they decrease to 0. Then the sum, if I add one and then I subtract the next, and then add the next and subtract from n equals 1 to infinity, converges. Okay. So for example, we can't compute this yet, but I can tell you that the sum of negative 1 to the n over n from n equals 1 to infinity converges. Okay, this is because setting C sub n equal to 1 over n, we can use the alternating series test. Alright, so let's prove this alternating series test. And let me show you the picture first. So let's look at this. The first thing I'm going to add, I'm going to kind of start up here. I'm going to go out to the right C sub 1. Right. So C sub 1 is over here. And then what happens is from there I subtract the next term, but the next term is smaller than the previous one. So when I added and I went to the right by C sub 1, when I subtract and go to the left by C sub 2, I don't go as far as I had started at, right? I started at 0 and I went to the right to C sub 1, and then when I go to the left to from C sub 1 back C sub 2, I don't get back to where I started. And then when I add the next term, I don't quite get to C sub 1, so I get to here. And then when I subtract the next term, I don't get quite back to wherever C sub 1 minus C sub 2 was. And then I keep doing that, and I keep kind of doing this zigzag back and forth, and the area that I can zigzag down into has to get closer and closer to 0, and I end up at this this value, which is the sum of -1 to the n times c sub n from n equals 1 to infinity. That's what this value would be right here in the middle. So what we're going to do is we're going to prove that if I look at these intervals, let's say this interval here, we'll call this I1, this interval here we'll call I2, this interval here we'll call I3, and so on. These are closed. We'll take the closed intervals here, and so they're compact and they're contained in each other. And one of our theorems said that if I take a bunch of sort of intervals that are contained in each other and I take the intersection, there's something in that intersection. So this intersection is going to be non-empty. That seems like a good place to look for our limit point. The other part that we get is that the lengths of these intervals are equal to one of the c sub i's, right? So the length of the first one is c1. The length of this guy is c3. The length of this guy is c5. The length of the next one would be c7. And those lengths are decreasing to 0. So the width of this intersection has to be decreasing to 0, so there can be at most one point in that intersection. Okay. And we'll use those two things together to say that there is something in the intersection and there's only one thing in the intersection. That must be our limit. Okay. So let's now prove this. Okay, so we're going to let ik equal c sub k 2k minus 1 comma c sub 2k. So the right hand points are the positive ones, the left hand points are the negative ones. Just because I added c sub 1, I should want my first term to be positive. I'm going to put a plus 1 right there and a plus 1 right there, so that my first term is positive, my next term is negative. It doesn't really matter which one you start with. We can just sort of re-index things, but for my proof and my picture to match up, I'm going to put that plus 1 there. Okay, then I sub k is contains I sub k plus 1 for each k, and the length of I sub k equals, well, what's the new term? It's c sub 2 k. Goes to 0. By the intersection theorem, let me find you a reference for that. That would be 2.38. The intersection of these intervals is non-empty. It's not that difficult. I'll let you show it. Fairly straightforward. To show that each partial sum S sub k, let's say S sub 2k, is in I sub k. So the limit of S sub k must be in the intersection the width of the intersections decreases to 0 . So if there were 2 points, say epsilon apart, they would eventually not be in all the intersections. So there can only be 1 point. Which is the sum of the series. Okay, that's not as rigorous as some things we've done. If you want a rigorous proof of this, we can find it in chapter 3. 3.43.